In 6.4, we're going to compute volumes by what we call the shell method, or volume by shells. It's very important, again, that you have a picture whenever you're trying to figure out volumes. Whenever we do volume by shell, it's going to be opposite from what we did with the disk washer method. In disk washer method, if we rotated about the x-axis, our integral was with respect to the variable x. And if we rotated around the y-axis, our integral was with respect to the variable y. Shell is opposite. If we revolve our region around the y-axis, our integral is with respect to the variable x. Now notice that this integral is a little bit different. Whereas the disk method involved the area of circles, the shell method involves the circumference of circles. So this formula is a little bit difficult to explain without a picture. Let's look at example 1. In example 1, we're going to take this region in the first quadrant, bounded by the function cosine of x squared. Since it's in the first quadrant, it's bounded by the x-axis and the y-axis. So notice the volume that we're going to generate is going to rotate about the y-axis. All right, let's draw ourselves a picture. And now we're in the first quadrant, and we're going to rotate about the y-axis. So cosine of x squared starts at 1 and it comes down. So we're going to take this region here and we're going to rotate it about the y-axis. And then we'll be creating our volume. How we're going to compute this volume is we're going to look at what's called a shell. Now a shell is just a cylinder. And these cylinders are going to have a height that's a y value. Then we're going to keep building up these cylinders and filling in until we have ourselves a volume. Now when you look at a cylinder, which in this case we're calling a shell, these are hollow. They don't have a top or a bottom. It's just the wraparound part. If I was to open a cylinder, it would have the shape of a rectangle. Where this length of the rectangle would be the distance around or circumference of the circle. So let's just look at a representative shell back on our graph. So since it's the circumference of the circle, what we need to do to compute the circumference, which the circumference is going to be 2 pi times the radius, is we have to find the radius. So our radius corresponds to our x value. So instead of using 2 pi r, we're going to use 2 pi x. And when we look at the height of our cylinder, our height is a y value. So notice this height here. It corresponds to the y value on our graph. In our case, our y value is the cosine of x squared. So let's compare this to our volume formula. 2 pi x, that's the circumference of our shell, and f of x minus g of x, where f of x is greater than or equal to g of x, this is going to be our height. Okay, so we're just going to add up all these shells. Let's continue on with example 1. First of all, I'm going to be integrating from x is equal to 0. X is equal to 0 to this point here. So I have to figure out what that point is. That's where cosine of x squared is equal to 0. So cosine is going to be 0 when x squared is equal to pi over 2. So x is going to be the square root of pi over 2. And that would be this point here. The square root of pi over 2. So our volume by shells is going to be the integral from 0 to the square root of pi over 2. Our shell is 2 pi x. And our height is cosine of x squared. We're integrating with respect to x. So we have a problem here because the argument on cosine is x squared, and I don't know how to integrate that. So this is where I'm going to do a u substitution. I'm going to let u equal x squared. So du over dx is going to be 2x. Or in other words, if I was to solve this for dx, I would have du over 2x is equal to dx. I'm also going to change my limits of integration. If x is equal to the square root of pi over 2, that means u, which is simply x squared, will be pi over 2. If x is equal to 0, then u is equal to 0. So let's do our substitution. Our volume will now go from 0 to pi over 2. We have 2 pi x cosine of u, dx is du over 2x. So remember, we can't integrate until everything is in terms of u. But notice that the x's cancel, and in this particular case, the 2 will cancel as well. So our volume, I want it to be blue. Our volume is going to be the integral from 0 to pi over 2 of pi times cosine of u du. And now everything, including my limits of integration, are in terms of u. Now I could pull the pi out, and then the antiderivative of cosine would be sine of u, but I'll just go ahead and leave the pi in. So I'm going to evaluate this from 0 to pi over 2. So we have pi of sine pi over 2 minus pi of sine of 0. And sine of pi over 2 is just 1. Sine of 0 is 0. And my volume is pi. All right, so let's try some more examples. In example 2, our region is going to be bounded by our graph f of x, which is equal to the square root of x plus 1, and g of x, which is equal to x squared. It's also going to be bounded by the lines x is equal to 0, x is equal to 1. So we want to find the volume of the solid generated by rotating r about the y-axis. So since we're rotating about the y-axis, that means I'm going to integrate with respect to x. So drawing a picture, I have my f of x is the square root of x plus 1. So it's the square root function shifted. And this would be f. My function g is x squared, so that's a parabola, vertex at the origin. Okay, these guys are going to intersect when x is equal to, I have no idea. And I don't really care, because this is also bounded by lines x is equal to 0, right? Which is just our y-axis, and x equal to 1. So we have this region that we're going to rotate about our y-axis. And then we'll have our volume. Oops, I always do that. So we'll have this volume. And to compute the volume, we'll go ahead and look at the height of a shell, and another height of a shell with a corresponding, right? So we're just creating this volume by looking at these shells that we're going to add up from x is 0 to x is 1. Okay. So sometimes it's helpful to draw a representative height so you could see which function is the upper and which is the lower function. And here I could see f is the upper function, g is the lower function. When I compute the volume, I'm going to integrate from x is 0 to x is 1. Two pi, remember the radius here for any one of these shells is just a corresponding x value. So 2 pi x. And then our radius is going to be upper minus lower function, which is the square root of x plus 1 minus x squared, okay, dx. So it looks like I can pull out the 2 pi. And then I'll go ahead and distribute the x and see what this looks like. So when I distribute the x, this becomes x to the 3 halves plus x minus x to the third. Okay, well, this one's not too bad. I can just go ahead and find the antiderivative or integrate. I'll have x to the 5 halves over 5 halves, which becomes 2x to the 5 halves over 5 plus x squared over 2 minus x to the 4th over 4. So I'm evaluating this integral from 0 to 1. So if x is equal to 1, we have 2/5 plus 1/2 minus 1/4, and we just subtract the 0 plus 0 minus 0, which I didn't really have to write. Now when we compute inside the bracket, it should be 13 over 20. So this is 2 pi times 13 over 20. And then our final answer will be 13 pi over 10 once we reduce our fraction. Right, so that's our shell method. But remember, we can also compute volumes by integrating with respect to the variable y. So if you're going to revolve your region around the x-axis, then the integral is going to be with respect to the variable y. In this next example, our region is in the first quadrant. It's bounded by the curve square root of x minus 1. The y-axis, the lines y is equal to 0, y is equal to 1. So we want to find the volume of the solid when we rotate about the x-axis, which using shell means I'm going to integrate with respect to y. Again, I want to draw myself a picture. F of x is the square root of x minus 1. So that's a square root function shifted over 1. So this would be my f. It's going to be bounded by the y-axis. The lines y equal to 0 and y equal to 1. All right, so now I can get a nice picture of this region that will be rotated about the x-axis. So we're going to create this volume with my sad picture where our shells are going to look something like this. So our shells are going to be on their side. So let's think about this. That means the height of a shell is this x value, right? The height of the shell corresponds to an x value. The problem is my function, my f of x, which is just y, is written in terms of y, not x. So I need to solve this for x to get x equal to y squared plus 1. And that would be my height. All right, so how do I find the radius here of my shells? Well, the radius is going to be a y value. And we're integrating with respect to y, so that's not really a problem. We'll just be replacing, going back to our volume formula. Instead of looking at 2 pi x, we have 2 pi, our y value. And then this would be the height of our shells. Our volume is again with respect to y. We're going to be integrating from y is equal to 0 to y is equal to 1. This will be a 2 pi y, and the radius is y squared plus 1 dy. I can go ahead and pull out the 2 pi and then distribute the y, and I'll see what it looks like. So integral from 0 to 1, y to the third plus y dy. And then that becomes y to the fourth over 4 plus y squared over 2, evaluated from 0 to 1. And we have 2 pi times 1/4 plus 1/2, and then minus 0. That would be 2 pi times 3/4. And our final answer reduced will be 3 pi over 2. All right, so we're going to just do one more example of this shell method. In example 4, we have this region in the first quadrant. It's bounded by the curve f of x equal to 3 minus 4x, the y-axis, the lines y is equal to 1, y is equal to 2. So we're going to find the volume of the solid obtained by rotating our region about the x-axis, which tells me I'm going to integrate with respect to y. Again, let's go ahead and draw ourselves a picture. So our function f of x is a line going down, looks something like this. And then we have our y-axis. Again, we're looking at the first quadrant. Our function, the lines y equal to 1 and y equal to 2. Okay, so here's my f, y equal to 2, y equal to 1. Here's my region that I'm going to rotate about the x-axis. So I would get this volume. Let's see if I can just see what this would look like. Maybe it'll help if I fill this in as well. So if I look at a representative cylinder, it would look something like this. So the height of the cylinder is an x value. So I need to solve my function f of x in terms of x. And the radius corresponds to a y value. So we're going to fill this in from y is equal to 1 to y is equal to 2. Again, we're just going to fill it in with the cylinders or shells so that we can create this volume. Well, first of all, y is equal to 3 minus 4x. And I need to solve that for x, which gives me 4x equal to 3 minus y. And then x is going to be equal to 3/4 minus y over 4. So our volume from y is equal to 1 to y is equal to 2 pi y, and then we have 3/4 minus y over 4 dy. Pulling out the 2 pi, let's see, if I did multiply through by the 2, you know what, instead of pulling out just the 2y, I think I'm going to pull out 2y and also 1/4, just to get rid of the fraction. So that will leave me with y times, factoring out a 1/4, this would be 3 minus y. And then distributing the y. On the outside, I'll have pi over 2. In the integral, once I distribute the y, it becomes 3y minus y squared dy. And you didn't have to. You can always keep the constants in. You never really have to pull them out. So I have pi over 2. This is going to be a 3y squared over 2 minus y to the 3rd over 3, evaluated from 1 to 2. So pi over 2 on the outside. Inside I have y squared. If I put in 2, that's 4 over 2, which is just 3 times 2 or 6, minus 8/3 minus 3/2 minus 1/3. What is that? 10 over 3 minus 7 over 6. Okay. So this would be 13 over 6 times our pi over 2. It doesn't look like anything will reduce, so it looks like it's going to be 13 pi over 12. And this is our last section for the semester, and this is the shell method. All right, so this is it.